Section 6.5 is linear inequalities. I can graph linear inequalities in two variables, and I can use linear inequalities when modeling real-world situations. Big ideas for this section. A linear inequality in two variables has an infinite number of solutions. Solutions to a linear inequality in two variables can be represented in the coordinate plane as the set of all points on one side of a boundary line. In example 1 here, we're going to try and figure out if these ordered pairs are solutions of the inequalities. So, remember that ordered pairs are x and then y, and we're going to plug these in for x and y just like we did when we were checking for solutions of equations. My x goes in my x spot, the y goes in the y spot. So I have 2 is greater than 1 minus 3. Reduce here, 1 minus 3 is negative 2. Is 2 greater than negative 2? Yes. So is this a solution? Yes. Same idea here with b. X goes in for x, and the y goes in the y spot. So y is negative 7, greater than x is negative 3, minus 3. Simplify over here, I get negative 6. Is negative 7 greater than negative 6? No. So since that is not true, it is not a solution. Go ahead and pause here and give this one a try if you'd like. Now, same idea here. We're going to plug in our x in our x spot and our y in the y spot and see if it's true. If it's a true statement, it is a solution. If it's not a true statement, it is not. So I see a y, so I plug in a 6, less than or equal to 2/3. I see x, so I plug in 3. And remember, if there isn't a sign there, our operation is multiplying. When I multiply here, I can set it up as fractions and multiply across 6 over 3, which is 2. Add, and I get 6. Is 6 less than or equal to 6? Yeah. It doesn't have to be less than. It can be either one. So it can be equal to or it can be less than. It just has to be true in one way or the other. So because it has this cute little equal to line right here, it means it can be equal to, and here 6 is equal to 6. So yes, this is a solution. The graph of a linear inequality in two variables contains all of the points in the coordinate plane that represent solutions. So it's a little bit different than the graphs of linear equations. Equations still have every point that's a solution, but it's just the line. Here when we're talking inequalities, it can be any point that satisfies that. So it could be any point less than your line or greater than your line or whatever your inequality happens to be. The graph is a region, and it's called a half plane that is bounded by a line. So we draw in our line just like we would if it was an equals to an equation, but then we shade in our half plane to show all of the answers that could make it true. So all points on one side of the line are solutions, and all points on the other side are not. So it's all or nothing here. It either is or isn't, and it's that entire side of the line. If we look on the top of page 395, here they have a couple examples. So on the left, they have the equation, or inequality, y greater than 3 over 2x minus 1. So they still started at the intercept, negative 1, and went up 3 over 2 with their line. The difference here is that it's a dotted line, okay, because it's not equal to. So we just use that line as a separating point, but those points aren't on that line. If we look at our inequality, it doesn't have the little equal to line. So it's a dotted line. And we want all of our y's to be greater than our x's. And so if we look there, they shaded above there. So the yellow shading is all of our solutions. And the second one on the right there, they have y is less than or equal to negative 3 over 2x plus 1. Okay, so here our line is solid because we have the equal to. So those points are included, they are solutions. And because I wanted less than, they shaded below the line. Less than is lower. In example 2 here, we're going to graph an inequality in two variables. What is the graph for our equation here? Y is greater than x minus 2. We are still going to start at our intercept. And remember, that's our y-intercept. So it's where it crosses the y-axis. And that's at negative 2. We're also still going to use our slope. And our slope here is 1. If there's not a number in front of our x, if there's not a visible coefficient, we know it's 1. And if our slope is 1, we can write any whole number as 1 over 1. So our rise is 1, our run is 1. Up 1 over 1. Up 1 over 1. And I'm going to continue this pattern here. If we look at our inequality now, okay, so what we've done so far is the same as we've done last chapter. The difference, though, is we need to check our inequality now. If we look here, our inequality doesn't have an equal to line. So it's not going to be solid, it's going to be dotted. And that's part of the reason I extended my pattern here. If you accidentally draw in your line and are trying to erase it and it doesn't seem pretty clear, just write that it's dotted, okay? So that we can tell the difference there. And you would still use your straight edge here to extend that. So there's our line. Now we have an inequality, which means it's not just things along this line, it's any point that could make it true. So since we have a greater than here, we're going to shade above. Greater means bigger, means above. So our solutions is going to be everything above our line. Couple ways we can tell that here. We can pick a point. Let's say I picked this one. And I want my y values to be greater. Okay. So instead of being at 0, I want 1, 2, 3. Those are bigger. Instead of being a y value at 3, I want them to be bigger. 4, 5, 6. We go up. And remember, if there's one solution, it means they're all solutions. So since I went up there, every solution in this part works. The other thing we can do is we can use a test point. We can pick any ordered pair that's not on our line. Here I'm going to pick 0, 0, okay, because that's fairly easy to plug in and to check. 0 greater than x is also 0, sorry, minus 2. 0 is greater than negative 2. Is that true? Yeah, 0 is bigger than negative 2, which means 0, 0 is a solution. So since 0, 0 is a solution, everything on this half plane is a solution. Remember, it's the entire half plane. If 0, 0 was not a solution, then we'd have had to shade the other side. So a few different options there on how we know which direction to shade. But the big thing is to plot our line the same way that we have before. So use your intercept and a slope, or find both your intercepts or a point and a slope, whatever it may be, and go from there. Check your line. Is it going to be dotted or solid? Here it was dotted because it didn't have the equal to. And then greater means we're going to go up. Less than is lower. Feel free to pause here and give this one a try. Okay, I'm going to start at my intercept plus 1. And remember, that's on my y-axis. My slope here is 1/2. That's my rise over my run. My rise over my run. We could also go down and backwards instead if we make them both the opposite. Okay, do a real quick double check. Slope is positive and it's going up, so we know that we are at least on the right track there. We can connect our dots here because, our inequality has that equal to line. So it's going to be a solid line. Make sure you put your arrows to show that the line continues. Now we need to check, are we going to shade above or below? Again, a couple different ways we can do this. We can look at it and say less than means lower. So less than and lower means we're automatically going to go below our line. Okay, we could also pick a point, any point, and we want our y value to be less than that. So instead of being at 1, we want it to be less than, like 0, 1, 2, 3. Instead of being at 3, we want it to be lower, like 2, 1, 0. Okay, since we shaded below, that means we're going to shade all of it below. The third way that we can do this, guys, is with a test point. So we can pick any point that's not on our line. Again, I'm going to pick 0, 0. Because those numbers are easy. We can always use 0, 0 unless our line goes through that point, but I could have also used 6, 7 if I wanted to. I could have used pi 3.14, negative pi 3.14. Whatever it happened to be, I just use 0, 0 because those numbers are fairly easy to work with. So I plug a 0 in for y and a 0 in for x. Multiply to 0, add 1. Is 0 less than or equal to 1? Yeah. So since 0, 0 is a solution, everything on the side with 0, 0 is a solution. So again, 3 different ways that we can check there to see if it's a solution, but they will all work. In example 3 here, we're going to keep going with graphing these. The difference is these only have one variable. So if we look here, x lines are vertical. It's all the x values that have -1. So -1, 0. We could go -1, 3. We could go -1, -3. Okay. Remember, it's going to be a vertical line. It's a dotted line because it does not have the equal to. Okay, it doesn't have that little equal to line, so it's going to be a dotted line. Dotted vertical line here. And you'll use your straight edge to do this as well. Now, I want my x's to be greater than -1. So it's not necessarily just an up and a down here, but x's to be greater than -1 are x's like 0, 1, 2, 3. So since these are solutions, I'm going to shade this entire half plane. We can still check ordered pairs as well if we'd like. We could check like 0, 0. I only have an x though, so is 0 greater than -1? Yes. So since this is a solution, all of this is solutions. Same idea here with b, except it's a y equals lines. And remember that y lines are horizontal. It's all the y values that are 2. So on my intercept at -4, 2, at 3, 2, okay? Here it's a solid line because it's equal to. So we can use our straight edge here. Draw our line in. Arrows. And here it's greater than, so that's going to be above. Okay? Everything above. If we weren't sure, we could use a test point. Again, we could check 0, 0. The only thing I can plug in there is a 0. Is 0 greater than or equal to 2? No. So since 0, 0 is not a solution, I can't shade this half plane here. And I have to shade the other one. So my solutions are everything above there. And I'm going to stop section 6.5 here, and we'll continue with another video.